Of you. So if you don't have your periodic table out, now would be a good time to do that. All right. When it asks, where is the most active metal located? What are you going to say? Francium. Whoops. Whoa. Hello, headquarters. What happened here? All right. Francium, which is located where? It's in group 1, but where in group 1? Group 1 is on the left side, on the bottom. Okay, so the most active metal is going to be at the very, 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 very bottom of group 1. So it's going to be francium. All of group 1 is going to be active. Very active. So active, in fact, that if you're wandering down the street, you're never going to see these guys just hanging out. They're so active, they're going to react with the atmosphere. They're going to just react with anything they can find in order to get rid of that electron as quickly as possible. All right, where are the most active nonmetals located? On the right side. Okay, where on the right side? Top. Okay, so you mean helium is the most active nonmetal? Because that's the top on the right side, right? Look at helium. It's up here. It's at the top of the right side. Is that the most active nonmetal? No. Why not? It has a full valence shell. So none of these are included in the most active nonmetals. These are the noble gases. So fluorine is the most active nonmetal. I'll put a little F here for fluorine. All right, as you go from left to right across a period, the atomic size, you cannot do this one yet. I told you to skip it. We're going to talk about that in a few minutes. All right, we can, however, do number 4. As you travel down a group, you got to think, the atomic size increases or decreases and why. So let's take a look as we're going from top to bottom down a group. Let's take lithium all the way to francium. Lithium, sodium, potassium, rubidium, cesium, and francium. What happens to the size of the atom as you go down a group and why? Got to think. Why?
It increases because they're being protons, or just going up in protons.
Well, it is going up in protons, but protons are really, really, really small. So you're on the right track, but let me just write down, you're right, it does increase, so write down it increases. And then let's look at what's happening as I go from lithium all the way down to francium. Oh. Okay, hold on. I'm going to pull out my periodic table so it's in front of me. I don't want that blue one. I want a white one. Okay. So first thing we're going to do is we're going to talk about how would we measure the size of an atom. So if I draw an atom, here's my nucleus. Look how cute that little nucleus is. Isn't it cute? And then around that nucleus, we have these energy levels. Correct? So when we measure the size of an atom, we are measuring it from the nucleus to the outside energy level. That's called the atomic radius. Just like in math. The radius is measured, the radius of a circle, okay, is measured from the center to the outside. That's the radius. So the atomic radius is measured from the nucleus to the outside energy level. So let's say this is lithium. And I'm saying it's lithium because it has 2 energy levels. In the first energy level, you have 2 electrons. And in the second energy level, you have 1. Does everybody know where I'm getting those numbers from? You can't see? But right here, 2-1. Okay? Your periodic table should be in front of you. Now let's go all the way down to francium. There's a lot going on in here, but let's do francium. So here's francium's nucleus. How many energy levels does francium have around it? 7. Look at those perfect circles that I drew. Okay? They're perfect. Just say that they're perfect. Okay. So if we're going to go from the nucleus all the way to the outside energy level, okay, which one is bigger? Francium, because it now has 7 energy levels, whereas lithium only had 2. So, what happens to the radius as I go down the group? It increases. Why? You get more energy levels, not electrons, energy levels. Okay? You can't say electrons, and the reason you can't say electrons is because if you look at, let's say, francium and radium, they're right next to each other down there in the bottom left corner. Radium has more electrons, but it's actually smaller than francium. Okay? I'll explain to you why in a little while. Let's just look at from the top to the bottom. Does everybody understand why it's getting bigger as you go down? You're adding more rings. So the more rings I add, the bigger my atom is going to be. So if we go back to our sheet here, it says, as you travel down a group, the atomic size, we're going to say, increases because we are adding more energy levels. Skip number 3. We'll get back to that in a little while. Okay? All right. You got your thinking caps on? A negative ion. So let's think about what a negative ion is. Oh, go ahead. Give me an answer.
Is it larger because it has more electrons?
It is larger, and it is not necessarily because it has more electrons. However, that is true. It does have more electrons. So your thinking cap is on. Let's go get a new piece of paper. So let's take a fluorine. Okay? Fluorine has a nucleus here, and it has 2 rings. Energy level, energy level. Okay? And it's going to become a negative ion. I got to put some electrons on here. 1, 2, and then 1, 2, 3, 4, 5, 6, 7. Okay? So here's the nucleus. Let's make the nucleus black like that. Okay. So now you're telling me that when this fluorine becomes a fluorine ion, it's going to become F-1. And that F-1 means it's going to gain an electron. So if I put that there, yes, it is gaining an electron. But electrons are so small that by gaining that electron, it doesn't change the size of the atom. However, you just shoved something else onto that ring. You ever have a bag of something and you try to shove one more thing into the bag? What happens to the bag? It expands. So, if all of these little negative electrons are on here, and I shove one more electron in there, the electrons are negative and they're going to repel one another. And when they repel each other, this electron shell gets a teeny tiny itty bitty bit bigger. And so when we form a negative electron, we actually get larger because of what we call electron-electron repulsion. I do not expect you to know that yet, but now I do. We are repelling, these electrons are repelling each other so that this ring gets just an itty bitty bit bigger. So yes, you're adding an electron. You're getting bigger because those electrons are repelling each other. Understand? Okay, so let's go back to that question, wherever the heck it was. Yes, it is getting bigger. So now, a positive ion, that means an ion that is losing an electron. I want you to think before you answer. Is it getting bigger or smaller? And why? Is your brain turned on? You guess. All right, look. Let's take one that's give me any element that's going to become a positive ion. Okay, lithium. I like that you picked something nice and small. You made my job easier. All right. So here's lithium, and it's got how many rings? 2. Okay? In the first ring, I've got 2 electrons. In the second ring, I have 1. This is a lithium atom. When it becomes a lithium ion, we already said it's going to become a positive 1, right? How did it become a positive 1? It lost an electron. All right, so let's lose an electron. Whoops, that's losing a lot of electrons. All right. Why did the lithium ion become smaller? Joe? It lost an energy shell because that shell is now empty, so it is gone. Okay? So you become smaller because you lose a shell. You become bigger because the electrons are repelling one another. Got it? All right. I asked you to skip 7, 8, 9, 10. We're going to get to that today. All right, elements of group 1. What the heck are those called? Alkali metals. That is a big fat pen. All right, alkali metals. What are elements of group 2 called? Alkali earth metals. Elements of 3 through 12 are called the transition metals.
No. Yeah.
As you go from left to right across the periodic table, the elements go from what to what? Metals to nonmetals. Excellent. Group 17 are called the halogens. What's the matter out there? You guys getting okay? What's the most active metal in group 17? Fluorine. He's the bully. What are the group 18s called? Noble gases. All right. Easy peasy lemon squeezy. I crossed off number 18. Okay? We good? Okay. Elements within a group. Which way do groups go? Up and down or left and right? Up and down. They have the similar number of valence electrons. If you do not know this yet, you need to know it right away. They also have similar chemical properties. I don't know if I can fit it all in here, but write that down. They have similar chemical properties in the same group. What elements in the same period have the same number of? Good. Same energy levels. Okay? So everything in period 2 has 2 rings, 2 energy levels. Everything in period 3 has 3, and so on and so forth. What? We had a question? We good. Okay. Where do we find the colored ions? Where do we find ions, that means they're either positive or negatively charged, that have pretty colors? That is when the metals are going to give off energy. But somebody said it. Where do we find the ions that have pretty colors? Transition metals. All right, as you go down a group, The elements generally become more or less metallic. They use the word metallic character for this. More metallic as you go down. My friends over here on the left side, you okay? All right. In the majority of elements on the periodic table, are they metals or non-metals?
Metals.
Metals. We love it. Elements on the periodic table are arranged according to, Jack? Atomic number. And that's the periodic law. And then an element with both metal and non-metallic properties is called a metalloid. Flip it over. All right, here we go. Shayla, which one's the alkali metal up there? What letter? No, what letter? Up on the top. Welcome back. Okay, hold on a second, the hot rod. Let's think about what the question says. An alkali metal. Is hydrogen a metal? Okay, so that can't be the answer. Do you know where the alkali metals are?
Yes.
Where are they?
In first grade.
Okay, so now your answer choices are either I or C.
Oh,
Okay. Whew, that was rough. All right, alkali earth metal. What group are those in? Group 2. So which one's my alkali earth metal? F. Which one is an inactive gas? I like A. Okay, inactive means they're a noble gas. A is the only one there. All right, an active non-metal. H, as in ha ha ha. All right, which one's the semi-metal? B. All right, number 6 says an inner transition element, which means there's 2 choices here that I'll accept either one of. Which one are your transition metals? E or D? E or D? Now the answer is D, and the reason it's D is because it's a transition metal. Remember I said that these lanthanide and actinide series, when you were coloring them in, are in here? They're kind of inside those transition metals. That's why they call them inner transition metals. So I'm going to put a D here, even though I would have accepted E. Most common oxidation state is -2. Oxidation state is the charge. Nora, which one has a -2? What? Which one? Well, do you have a periodic table in front of you? Okay. Let's find a column on the periodic table that is going to form -2 ions. G. Okay? So, if you look at your paper here, okay, it's going to be in group 16. These guys are going to form -2s. That G happens to be oxygen. So that's going to be G. All right, a metal with more than one oxidation state. Those are your transition metals. Your transition metals are going to have multiple oxidation numbers, like iron and manganese and chromium and vanadium. All of those have lots and lots of choices. All right, which one has an oxidation number of +3, Lila? Nope. Well, E would have one, wouldn't it? Hold on a second. But that's not what they were going for here. So yeah, you can take E. Give me another one that's going to have an oxidation number of +3. Group 13 is going to be all +3s. So, because we used E for another one, I'm going to go with J here. But yes, E, I would take E. If you wrote it on a test, I'd take E because it does say +2 or +3 for cobalt there. All right, which one has both +1 and -1, Christian? I, which is hydrogen. All right, here we go. New stuff. You ready? Okay, I'm going to just cross this stuff off because obviously when I used this template, I didn't change those things down there. We are going to talk about periodic trends. One reactivity we kind of already talked about. The most reactive metals are in the bottom left. The most reactive nonmetals are in the top right. What's a trend? Yeah, what's a trend? You guys like, oh, it's trending on TikTok, right? Isn't that what you always say? Oh, it's trending on TikTok. Give me a trend that you guys like are doing right now. Ask Joe. Yeah. Joe's a trend? Yeah. Alright, I'm going to start my own trend, right? So I'm going to come in tomorrow and I'm going to be wearing a red clown nose. And then on Thursday, Blessed's like, that is the coolest thing I ever saw. I want to be just like Miss Kaufman because she's so cool. And she's going to wear a red clown nose. And then next thing you know, like you see 4 people in the hallway all wearing red clown noses. And then the next thing you know, the whole building is wearing red clown noses. And then the next thing you know, all Port Jeff Station is wearing red clown noses. That's a trend. It's going in a certain direction. Ryan thinks I'm crazy. Would you wear a red clown nose if I asked you to? Hey, listen, there's been crazier trends out there than red clown noses. Okay? Like Stanley Cups are a trend, right? Just carrying a water bottle was a trend. When I went to high school, nobody carried water bottles. But then somebody decided they were going to carry a water bottle. And somebody else is like, oh, that's so cool, they're carrying a water bottle. And the next thing you know, everybody's carrying a water bottle. A trend is just something that's going in a certain direction. They don't last forever, but that's what they do. So if you look at reactivity, let's go back to our periodic table, and let's just look at this column right here. Group number 1. Lithium, sodium, potassium, rubidium, cesium, and francium. They are all active metals. However, as I go from top to bottom, do they get more reactive or less reactive? More. That's the trend. The trend is they are getting more reactive as you go down the group. What happens to the reactivity of a nonmetal as you go down a group? Less reactive. So reactivity, we can look at trends. We can look at the trend within a group. We can also look at the reactivity trend as you go across a period. Okay? So let's look at metallic character. As you go from left to right across a period, what happens to the metallic character? What's the trend? Less metallic. That's a trend. Okay? So that's kind of like reactivity. We're going to look at atomic radius. That's the next one we're going to look at. And now you know how we're going to measure radius, right? It's going to go from the nucleus to the outside electron. Okay? Let's look at the radius going from lithium all the way down to francium. I'm going to draw up here for a second. Okay? So here's lithium. There's his nucleus. He's got 2 rings. We look at sodium. Sodium has 3 rings. We look at potassium. It has 4 rings. I'm going to run out of room here. Let's go down to francium. How many rings does it have? 4, 5, 6, 7. What happened to the radius? What's the trend of the radius as I go down the group? It gets bigger. Why is it getting bigger? You're adding more energy levels. Okay? Now, that's not something you kind of have to memorize, even though it's not that hard. Okay? You could also turn your reference table to table S, as in Sally sells at the seashore. Take a look at table S. And I want you to look at the very last column on the right-hand side. See where it says radius? There you go. Good job. All right, everybody got table S open? What? No reference table? Killing me, kid. Anybody else need a reference table? All right, very last column. Whoops. You go to the very last column. It's going to look like this. Okay. Okay. Right here, atomic radius. Let's go to lithium. Lithium's atomic radius is 130. See it? Rubidium's atomic radius is all the way down here. Where is it? What's the atomic number of rubidium? You got it in front of you. RB, what's its atomic radius? Oh, there it is, 37. Is that right? 215? Okay. So, if lithium is 130, and this is, I forgot already. What was it? Come on. Say it again. 215. Okay, so there's 215, there's 130. What happened to the radius as you went down? Got bigger. Do you need to memorize it? No, because it's right there on your reference tables. You just have to look. Now, let's look at the radius as you go from left to right. I'm going to actually duplicate this one. Can I duplicate that? Duplicate. All right. Now I have it. Okay. What do you think, before you look anything up, what do you think is going to happen to the radius as I go across a period? It's going to be inconsistent, okay? So let's say I'm wearing my red clown nose, and then remember Blessed went and she bought herself a red clown nose because she thought it was the coolest thing ever. And then Mr. Valerio comes in here and he's like, you guys are all crazy, why are you wearing red clown noses?
Yeah, that's very true.
That is very true. And he's like, I'm not wearing a red clown nose. But then Lily's like, you're not cool, Mr. Valerio. You need to be wearing a red clown nose. And so the trend, we're talking about trends.
Okay.
You going against the trend doesn't stop the rest of the trend, does it? Okay? So just because there's an outlier, thank you, Mr. Valerio, just because there's an outlier doesn't mean that the trend is not there. The trend is what's happening in general as it goes across the period. So yes, it's going to go up and down, up and down, up and down. But when we look at trends, we want to look at what it starts at and what it finishes at. Okay? Do we have only a couple minutes left? Is that where you're leaving me?
Yeah.
Okay, perhaps. Let me finish this one thing. What do you think the trend is as you go across a period? We cannot say it goes up and down, up and down, up and down. We can say it either increases or it decreases. What do you think? You think it increases. Okay. Let's look. What's the radius of lithium? Wasn't it 130? Okay. What's the radius of fluorine? 60. What happened to the radius as it went across the period? It went down. Why do you think it goes down? It gets what? It gets teensier, tinier. There's the same number of rings. So that's a problem, right? Why do you think it got smaller as you went that way? What are you changing as you go across? Number of valence, true, but what else? Starts with a P, ends with a proton. The number of protons. So now, if lithium only has 3 positives in its nucleus, think of it as a tug of war. And this lithium has 2 rings. 3 positives are pulling on 2 rings. To be continued tomorrow, my friends.